Let's now explore an example that takes into account three variables. We'll also look at one that takes into account all four of the variables, and we're not going to be able to visualize that. So that is specifically where PCA can become very powerful, is when we do have lots of variables and we're just trying to make sense of it. Already in R3, if we now look at not just blood sugar and BMI, but we look at blood sugar, BMI, and cholesterol from our toy data, and we just take a look at that in three dimensions, it's sort of hard to make heads or tails of this because it's hard for us to visualize where exactly these points are floating in three-dimensional space. So for us to be able to say, well, here's what's going on as related to these three variables, and so you can see we have blood sugar on this axis, BMI on this axis, and then cholesterol is up here, got a little bit chopped off. A little bit hard to make heads or tails of it. So as a result, we would want to produce a principal component analysis because our goal is to try to understand a sort of a linear relationship among these variables. By the way, that is what we are kind of doing when we're talking about PCA, is we're linearizing the relationship to some extent because we're coming up with eigenvectors. Remember, vectors are straight lines. So if we were to compute the variance-covariance matrix of this, we would see that we have our variances across the three variables. Now, this is the order in this ordered triple that I've laid out: blood sugar, BMI, cholesterol. So that's blood sugar, BMI, cholesterol in this order. And so this component here tells us the variance in blood sugar, the variance in BMI, and the variance in cholesterol. You can see that they're very different, and part of that just is going to have to do with scaling. If you notice the scaling, BMI is on a much tighter scale than, say, blood sugar, much higher scale there. BMI, you can see, is very short window there, and both blood sugar and cholesterol are in the hundreds, with ranging, about 30, 35 or so units. So BMI can throw that off a little bit, and there are some ways to correct for this, but we're not going to do that here. And then we can look at the covariances. So remember, these are the same columns and rows. By the way, notice one interesting thing, and that is that sigma, this variance-covariance matrix, is symmetric, meaning that if you take the diagonal and you look above the diagonal, so first row, second column is the same thing as second row, first column. First row, third column is the same thing as third row, first column. And finally, second row, third column is the same thing as third row, second column. So those are identical because the variance and covariance, or the covariance between two variables, doesn't matter which one you look at it, you're pairing them together. So sigma is symmetric, and this is partially the reason why this method does what we claim it does, which is the principal components, or the eigenvectors, tell us the direction of maximal variance in descending order of the eigenvalues. So this is an important feature that makes this mathematics all work out, but we're not going to analyze that in this particular video. So we would proceed as before. We would get our eigenvalues of this matrix. So this is the eigenvalues of this matrix, and then down here we'll have the eigenvectors of that matrix. So it's always on the variance-covariance matrix. I shouldn't say always, but always for us. Okay, so look at these principal component eigenvalues. So for PC1, remember that's the vector. For the first eigenvector, its corresponding eigenvalue is about 122. Okay, for the second eigenvector, about 67, and then about 4 for that third principal component. Now, if you sum these together right here, the sum is 192.5. And so now if we take 122 out of that 192, that gives us about 63, almost 64% of the overall total variance is given by principal component 1. So that explains a large portion of the variability in the data that we're seeing. The second eigenvector only contributes about 35%, so actually, well, that's about a third. And then the third eigenvector contributes very little to our understanding of how and why the data varies. Now, here are the corresponding eigenvectors. Now, keep in mind, this one we said was about 64, 33%, and very little going on here. So how do we analyze this? So do we say something like, by the way, if they're all negative, then you could also describe them as all positive. So does this mean that an increase in remember we have blood sugar, we're always going to have the order of blood sugar, BMI, and cholesterol. So in that order. So does this mean that a 0.66 reduction in blood sugar correlates with a 0.15 reduction in BMI and a 0.7 reduction in cholesterol? Well, not necessarily. This is just the vector that points in the direction of maximal variance. And to show you what that would look like, the blue vector here is PC1. There's a close vector to that PC1, PC3 here. It's kind of hard to distinguish where that's pointing exactly, but PC3 is that little green one, PC2 is that orange one. You can actually kind of see, if you think about it, the data seems to be spread out mostly in this direction. And then PC2 says our second direction of maximal variance is this one. Keep in mind that those are going to be orthogonal, and we could just double check that if we add up, if we take the dot product between V1 and V2, we should get 0. All right, and so the way that we might go about interpreting this, because it did seem like we were interpreting it somewhat of a linear regression type of way in our first example, and we want to refrain from that, right? Because the data is, we're not necessarily saying that this is the relationship among the three variables. This is just the relationship among the three variables in the direction of maximal variance. So this is the relationship in direction of max variance. Okay, so we would, if we look at these, we see that BMI has very little contribution. So here's how I would go about analyzing this. Other than to say a 0.66 increase leads to a 0.15 increase leads to a 0.73 increase. I mean, technically that would be okay, but the direction of maximal variance suggests that there's a strong relationship between blood sugar and cholesterol in that direction. So in the direction of maximal variance, we could say that this is some sort of indicator of, I don't know, what we might well, we might say that this is some sort of like risk factor, right? That this indicates that there's a strong relationship between blood sugar and cholesterol. So we might say that there's a mild or small contribution of BMI, and there's a sort of a strong contribution or strong relationship between blood sugar and cholesterol. So yeah, we can say that there's almost a 1-to-1 in the direction of maximal variance relationship between blood sugar and cholesterol. Keep in mind that the units are not the same, right? So the fact that this one is so small is likely associated or related to the fact that BMI is on such a small scale. But beyond that, we see that this sort of is perhaps indicative of some sort of like risk factor. Some sort of risk factor. Now, in medicine, they might have a better way of describing this principal component, but this is how we'll describe it here. Okay, that accounts for about 64% of the variance we're seeing. In principal component 2, the eigenvector, again, shows almost an irrelevant BMI. And in this direction, what we're mainly seeing is, notice it's somewhat the opposite of what we're seeing in this relationship here. This is suggesting that as your BMI goes up, your blood sugar goes up. Now this might seem kind of confusing because this one's blood sugar goes down, cholesterol goes up. Now, what does that mean, and why does that contradict what's up here? Well, keep in mind that these are in two different directions. This is the relationship that we are seeing in the direction of second, maximal variance. So if you look in the direction going in the direction of PC2, notice the relationship there. As blood sugar goes up, cholesterol is actually dropping down, right? Because we're kind of going across this way and then going down this way. In this eigenvector, we saw that as a strong relationship between cholesterol and blood sugar. Maybe it's a little bit hard to see, but as blood sugar goes up, cholesterol goes up as well. So that's what we're seeing in that direction of variance. In the third direction, remember, this is such a small contributor, it is almost negligible. And so this one just shows us that this is essentially just like a BMI weight, that this is some variance due to primarily just the BMI, where blood sugar and cholesterol are very low contributors in that direction. And that would be in this third direction, which is kind of hard to see here, but it's sort of perpendicular to both of PC1 and PC2. And that just accounts for very little variance, so it's almost a negligible eigenvector we want to take a look at. We haven't talked about this, but we've looked at the percentage of variance contributed that each principal component contributes. We often want to look at what's called a scree plot, S-C-R-E-E, not a screen plot, a scree plot. And what all that shows is it looks at the principal component number on the horizontal axis. Remember, and we always organize eigenvalues from largest in magnitude to smallest in magnitude. So PC1 is always going to be the highest. You should always see this either decreasing or, in some cases, if you have the same eigenvalue, then you might notice a flat spot, but it should never go up. And so you can see that of the overall variance, eigenvalue for principal component 1 is the highest, followed by principal component 2, followed by PC3. This is really useful if you have lots of eigenvalues and you want to kind of get a quick view, a quick relationship. This would be helpful if you had maybe say 30 principal components and you would want to see how many principal components do I need in order to explain, quote unquote, the most amount of variance. Again, these interpretations can be kind of fun. Since we're not experts in this data, it might be a little bit hard to talk about this, but some doctors might call this like metabolic risk. This variance direction shows like a relationship in metabolic risk. This second eigenvector kind of explains that relationship that we're sometimes seeing where the decrease in blood sugar leads to an increase in cholesterol. Okay, that does account for some of the variance. Maybe there is a subset of the population that they just have really low blood sugars. They tend to have a really low blood sugar, so they eat a lot more, unhealthy, fat-dense foods, and so maybe that bumps up their cholesterol. Maybe that's the second subset of people that we're seeing here. But the majority of people that we're seeing this relationship right here, where, again, there is a relationship among all three of these variables where an increase in blood sugar correlates to an increase in BMI and an increase in cholesterol. That is a true relationship. You can't necessarily look at the scale of these values other than blood sugar and cholesterol, because remember, blood sugar and cholesterol are kind of on the same scale. They're in the a range of about 30, but BMI is a much tighter scale. So just because this value is small doesn't mean it's negligible. It just means it in this direction is not as strong of a factor as blood sugar and cholesterol. All right, we'll stop here and we'll take a look at one more example where we can't really plot the data anymore, and we want to try to make sense of what we're seeing in our data. Lastly, I just want to mention that, again, remember we're studying variance. So does this talk about correlation or causation in any way? No, it just helps us understand how the data is spread out. And notice that we can pretty much get a good sense of how that data is spread out just by looking at PC1, maybe PC2. So in 3 dimensions, we only really need 2 vectors to explain the majority of what we're seeing. Perhaps in 10 dimensions, maybe the first 2 principal components explain the majority of the variance. So we can take something like 10 variables and only explain it in the span of 2, well, technically 10 by 1 vectors, but only 2 of them rather than having to deal with all 10 of them.